to the lecture series of optical instrumentation. This is lecture number 11, and in this lecture we shall complete the remaining part of light detectors. In previous lecture we discussed about lasers and quantum efficiency and responsivity of light detectors and PN photodiode. Okay. These are the topics: PIN photodiode, avalanche photodiode, photoconductor and phototransistor. So, this is the slide that we discussed in our previous lecture. So, photons are absorbed in all the regions over here in p type, in junction region, in n type, but only the photons that are absorbed in this region contribute to the output current. Only the electron and hole pairs that are generated in this region contributed to output current. Why? Because if any electron hole pair is generated in this region, then already there are a lot of holes present. So, the electron that is generated is absorbed by some other hole. Similarly, if any electron hole pair is created in this region, then there are a lot of electrons available in n type semiconductor. So, the hole that is generated, some other electron consume that hole. So, in output circuit we do not get anything. We want these electron and holes to be collected on the output terminals, then only we can be beneficial by the absorbed photon. So, that is why the electric field, you can see the electric field is this is the loss over here, it is going electric field distribution in p type region, in n type region, and most of it is in depletion region. Okay. So, variation in electric field. So, how can we overcome this? To increase the efficiency of the photodiode, more number of photons should be absorbed in the depletion region, then only we can get more current. So, how can we ensure that more number of electrons absorbed in junction region? By simply increasing the width of junction region. So, how can we do that? We can insert an intrinsic layer between p and n type semiconductor in the junction region, and that is why the next photodiode is called the next PIN. Pi stands for intrinsic. This can be achieved by increasing the width of depletion region, so that most of the incident photons are absorbed inside it. To achieve this, very lightly doped layer of semiconductor is inserted between p and n junction. It is so lightly doped that it is almost intrinsic, that is why I is used. Such structure is called PIN photodiode, where I stands for intrinsic. Okay. What is the benefit? Over here you can see the width of, now the photons that are absorbed from this end to this end will contribute to output current, because this is intrinsic layer. Any photon absorbed here, electron and hole will be generated. Okay. So, electron will go to this side, hole will go to this side. Okay, and we get output current. There is cavity, photon will come over here. You can see variation in electric field over here. More photons will be absorbed here. As we go deeper, the number of photons will keep on decreasing. Okay, that is why electric field is like this. And you can see the area under this curve is more if we compare it with PN junction photodiode. Okay. So, that is why this is more efficient than PN junction photodiode. This is the construction. As the middle layer is intrinsic in nature, it also offers high resistance, and hence most of the voltage drop appears across it. Okay. Such configuration results in drift component of the photocurrent to be dominating the diffusing component. Okay. As most of the incident photons are absorbed in junction region, or you can say I region. So, a double heterojunction PIN photodiode further improves the performance. As we have seen, heterojunctions are always better than homojunctions in semiconductors. So, you can see over here, this is a double heterojunction PIN diode. This is intrinsic layer of indium gallium arsenide. this is indium phosphide p type material, this is indium phosphide n type, and this is substrate of heavily doped indium phosphide n type heavily doped indium phosphide substrate. Okay. From over here the photons are incident and they are absorbed in this region, mainly the photons that are absorbed in this region contribute to output current, or we can say photocurrent. But in PIN diode there is no gain, there is no gain. So, for some applications this can be a disadvantage. The photodiodes that we are going to discuss after this, they also have some amount of gain. Okay. So, the current photocurrent that we get will be multiplied that with that gain factor. Despite this, there are still various applications in which PIN diode is used, like in audio CD players, DVD drives, etc. Also in optical fiber communication systems, this photodiode is used for detecting optical radiations. Okay. After PIN diode, next is Avalanche Photodiode. Now, what is Avalanche Photodiode or APD? They internally multiply the primary photocurrent through a multiplication of charge carriers. Due to this, the sensitivity of receiver increases because there is a multiplication factor. How this works? By using appropriate structure of photodiode, it is possible to create high field region within a diode. High field region is created inside a diode. This is done by using heavily doped heterojunction layers. Okay. So, what happens when this high field region is created? When primary electron hole pair generated by the incident photon pass through this high field region, they gain velocity, very high velocity. They get accelerated and acquire so much kinetic energy that they can ionize other electrons. They can ionize other bound electrons that are bounded with other atoms through striking, through collision. They can excite those electrons, they can ionize those electrons that are in the valence band. How? Through collision, and in the process they can create secondary electrons. So, secondary electrons are created due to this high field. Okay. And these secondary electrons, if there is enough voltage drop, they can again gain high kinetic energy and they can again collide with other electrons in valence band and they can excite them. So, in this way these electrons will be multiplied and we get more current, more photocurrent in the outside circuit, and in this way there is a multiplication factor. This phenomenon is known as impact ionization, because the accelerated electrons are impacting on another electrons that are in ground state and they are exciting those electrons to the from valence band to conduction band. If the field is high enough, the secondary carrier pairs may also gain sufficient kinetic energy to create again new pairs, and this effect is known as avalanche effect, and it can create carrier multiplication, and due to this avalanche effect the name is Avalanche Photodiode. Okay. RAPD is very commonly used Avalanche Photodiode. What is RAPD? Reach through Avalanche Photodiode is commonly used configuration for achieving this carrier multiplication. As you can see in this configuration over here, this is heavily doped, very heavily doped N type, and this is normally doped P type. So, over here very high electric field is created, and this is intrinsic layer, and this is again very heavily doped P type region. Due to this high electric field region, the electron and hole pairs that are created over here, this is electron this is a hole. Okay. So, electron will move in this side, hole will go this side, because this is reverse biased negative, hole will move this side, electron will move upward. Now, when electron will move upward, this is due to this high field region, it will gain enough kinetic energy and velocity, so that it can bombard, it can collide with other electrons, and it can create further, it can excite further carriers, further electrons. So, that is why this region is called gain region. Okay. Multiplication factor is M. It is a measure of internal gain provided by the device. It is defined by current after multiplication divided by current before multiplication, IM divided by IP, where IM is average output current after multiplication and IP is the primary photocurrent. Okay. This is called multiplication factor of Avalanche Photodiode. Now, like PN and PIN diode, the performance of APD is also described in responsivity, and it is given by eta E upon h nu, that is responsivity of simple diode, simple photodiode into multiplication factor. Okay. So, this is what is R for responsivity of simple PN or PIN diode into the multiplication factor. This is the responsivity of Avalanche Photodiode. Okay. Now, after Avalanche Photodiode, there is photoconducting detector. In photoconducting detector, photons are absorbed in all the region. There is no junction region. Okay. Like you can see in this diagram, there is a layer of N-type indium gallium arsenide semiconductor material. Okay. And over here, there are interdigital electrodes. Interdigital electrodes, one is connected with positive terminal and another electrode is connected with negative terminal, and due to this interdigital electrodes, if any like this photon is incoming over here, and if a electron and hole is created, if a electron and hole is created over here, then hole is electron is immediately absorbed by this and hole is immediately absorbed by this. So, this is the reason interdigital electrodes are used, so that more number of electron and holes can be absorbed, and because this is N-type region, so there are already electrons available, right. So, in photoconductors, the incident photon are absorbed by the conducting layer. So, this is conducting layer, due to which electron hole pairs are generated. Okay. And that is why they are called photoconductors. These carriers are swept by applied field towards respective electrodes, which results in the increased current in the external circuit. Okay. So, the current will be increased in the external circuit due to these interdigital electrodes, because they rapidly absorb those electrons. Now, we know electrons move faster than holes. So, electrons are collected faster, but holes are slow. Due to this, electrons are collected faster at the anode, while the corresponding holes are still proceeding towards the cathode, because holes are slower than electrons. What happens then? This creates an absence of electrons and hence a net positive charge in the region. This creates a positive charge in the region, net positive charge, and due to this more electrons are inserted from the battery terminal, and this further increases the current. This excess charge is compensated by the injection of more electrons from the cathode region into this region. So, from battery, more number of electrons are injected into this region due to this imbalance of negative and positive charge. So, this process leads to the generation of more electrons. this process leads to the generation of more electrons upon the absorption of single photon. A single photon is getting absorbed. As the photon is absorbed, the electron is swept away rapidly, but photon hole is slow. So, it has not been swept away till now. So, more number of electrons are injected. So, this leads to generation of more electrons. This effect is called photoconductive gain and it is denoted by capital G. This effect is called as photoconductive gain, capital G, and it is defined by the ratio of transit time of slow carriers to the transit time of fast carriers. So, what are slow carriers? Holes, and what are the fast carriers? Electrons. So, this gain is defined by the transit time ratio of the transit time of slow carriers divided by transit time of fast carriers, okay, because transit time of fast carrier is less and transit time of slow carriers is more. So, this is overall gain factor. So, what is photocurrent? In this case, photocurrent produced by photoconductor can be written as, this is in case of photoconductor, photocurrent is denoted by Ig and it is equal to photocurrent of a simple diode into this gain factor E eta P in divided by H nu, that we have seen in the formula of responsivity in our earlier class, into this gain. So, this is photocurrent IP into gain. So, there is a gain factor in photoconducting detectors or photoconductors. Okay. We know where eta is quantum efficiency of the device, P in is incident optical power and IP is photocurrent in the absence of any gain. So, IP is photocurrent of simple photodiode and Ig is photocurrent of photoconducting detector. So, Ig is equal to IP into gain of photoconductor. Okay. So, we have multiplication factor in avalanche photodiode and we have a gain factor in photoconductors. Why are they called photoconductors? Because there is a conducting region, conducting layer absorbed by conducting layer, photons are absorbed by conducting layer. Okay. Next and last is phototransistors. Phototransistors. So, as you can see, this is the symbol of a transistor and what is the symbol of phototransistor? Incoming photons, arrows towards base. Okay. Similarly, you can see this is a MOSFET or FET and incoming photons, okay, on gate terminal. This is how they look like. Phototransistors is basically same as NPN transistor with unconnected base. Unconnected base. So, base is not used in phototransistor or either BJT type or either FET type. Okay. So, you can see base is not given here, base is not connected, base is illuminated using from photons. Okay. Also, you can see in this picture there is no base, only collector emitter, only drain and source. So, base is not connected. So, principle is same as PN photodiode, the only thing is we are not connecting base. So, what is the benefit? Transistor has a gain factor. So, to use that gain factor, we are using transistor to detect current. This transistor is again made up of special material like photodiode, PN photodiode. Okay. Transistor has a amplification factor. Okay. Transistor current amplification technique provides internal gain. So, there is a gain factor due to amplification, internal gain of photocurrent in a phototransistor. Also in transistor, emitter base injection efficiency is good. Okay. Good emitter base injection efficiency is also provided by the phototransistor. Optical gain is given by eta into HFE. Eta is quantum efficiency and HFE, we know what is HFE is forward common emitter current gain. What is the disadvantage? They are non-linear and slow speed of response. This is the disadvantage of phototransistor. Okay. So, how we have, this is the comparison of photodiode and phototransistor. So, again it converts light energy into electrical energy and it is also semiconductor light photodiode, but it amplifies the current that is generated from light energy. It is basically light sensitive PN junction diode with an exposing opening or exposed junction for light. It is light sensitive BJT with exposed base region. Okay. It is made up of 2 layers, it is made up of 3 layers. In there is single PN junction, it has 2 PN junctions. Okay. It is only 2 terminal device, it can be either 2 or 3 depending on the design. In some designs there is third terminal also there. It only converts light energy to electrical energy. It also amplifies the current. Okay. Mainly diodes are used for in solar cells for generating current, and phototransistors are used in light sensing to sense the amount of light or intensity of light. Okay. Few more differences: photodiodes are less sensitive with comparison to phototransistor. Now, over here we have amplification factor, so they are more sensitive. Again, the response of photodiode is quick, fast, response is fast in comparison to phototransistor. Phototransistor, the response of phototransistor is slow. It does not require power source. Phototransistor may require power source for biasing also. It also requires for biasing, but very less. It generates both current and voltage, it only generates current, it is cheap, transistors are expensive. Lastly, photodiode is used for converting solar energy into electrical energy. This is the application. Phototransistors are used for sensing light in light sensors. Okay. So, this was about light detectors. We have discussed PN diode, PIN diode, Avalanche photodiode, photoconducting detectors, phototransistors. So, with this lecture, second unit of this subject is finished. We have divided the second unit in 2 parts. First we discussed light sources. Under light sources we discussed LEDs, various kind of LEDs, different LED structures, their uses. We compared surface emitting, edge emitting LED. Then after that, in light sources we discussed lasers, different kind of lasers we discussed, solid state lasers, liquid lasers, gas lasers, semiconductor lasers. These things we discussed in light sources, and after that in light detectors we discussed light detectors. So, this was all about light sources and light detectors. From next lecture we will start unit number 3, and in unit number 3 we will discuss interference and the components and the instruments that are based on mainly interference effect. Okay. So, thank you.